Dr. Karsten Kruse from Zoya.
Yeah, thank you very much. So I'd like to tell you about work, mostly at least about work that we did recently with Jean-François Journy, Jacques Pro, and Sriram Ramaswamy on the actin cortex. But I'd also use the opportunity to introduce you to some other aspects of our work. Now, I guess most of you know what a hydrodynamic description is. If not, I will tell you. Maybe you're a little bit less familiar with what the actin cortex is. So to start off with, I would like to just remind you that cells, biological cells, living cells, have really remarkable capabilities. They can move, they can grow, they can divide, they can take up nutrients. All these are processes that are really vital. I mean, without them, there wouldn't be any life. And all these processes that I mentioned are at least in part driven by the cytoskeleton. So before telling you what the cytoskeleton is, in case you don't know, I would just like to give you some examples to have at least some movies in here. So the first movie showing you a cell that is dividing. So you see basically a cell that has an egg shape, and you look onto the pole of a cell, and you see that in the cell a ring has formed, and this ring is contracting. And by contraction, the ring is really separating the cell into two, cleaving the cell, and then you have two daughter cells. This is a movie that you have seen if you have been yesterday morning in the seminar by Alison Chung. Then you have seen at least a similar movie to this one. This is a cell sitting on a substrate and crawling. I guess also Mitya was showing that, or Julia, I don't remember. But this is so the prototype of what crawling cell looks like. So you look on the top of a substrate where the cell is moving. And here on the bottom, you see a movie taken with a very high-speed camera of a sperm cell, where the sperm head has been attached to the substrate, and you see the nice wavy motion of its flagellum, which is needed at least in some part of the life cycle of the sperm to propel the sperm forward. So everything that I'd mentioned before, these motions, what cells can do, are just depicted here, and all of them are driven by the cytoskeleton. And so it's time now to tell you what the cytoskeleton is. So here you see a fluorescent micrograph where in blue you see the DNA stain, so this is not the cytoskeleton. But the green and the red stuff, they belong to the cytoskeleton. So the green things, they are so-called microtubules, and they are really small tubules made from proteins, quite stiff ones. They have a persistent length of about 1 millimeter. And they extend basically from the cell nucleus, the cell center, to the cell periphery, and thereby assure communication between the cell periphery and the cell center, so it allows the cell to communicate with its environment, basically. So it allows the cell nucleus to communicate with the cell environment. So these would be the microtubules. They will be of lesser interest for us today. Most work that I present today will be focusing around these other kind of filaments. They're called filamentous actin or F-actin. They're made of small globular proteins which are called actin monomers, or globular actin, G-actin. And you see them here also depicted in red, and you see them almost everywhere, but predominantly here towards the periphery of the cell. So these are the objects that we are mostly going to focus on. These filaments are usually semi-flexible in the sense that they have a persistence length of about 10-15 micrometers in a cell, and the length of these filaments, it's not really known, but it's supposed to be a half a micron, maybe up to a micron, maybe a little bit less than 500 nanometers. So these are the basic building blocks of the cytoskeleton, and obviously these things alone, if they were just usual passive polymers, wouldn't be able to perform all these tasks that we have seen before. There are two properties of these filaments that are really at the heart of the processes that you've seen before. One that is not very obvious from these images, but I just tell you, is that these are polar objects. Polar is not referring to any electrostatic charge distributions, but it's just saying that one end of these filaments is different from the other one. Here also one end is different from the other one. You can distinguish them structurally, and it has also some dynamic effects, as we will see. The second, and maybe to some extent at least more important feature, is that the cytoskeleton is really an active system. And by this I mean that energy is really fed into the system on the level of the individual constituents. And the individual constituents are, well, the building blocks of the polymers, the filaments, the actin filaments and microtubules, but you also have other proteins that interact with these filaments. For example, you have motor proteins. Motor proteins are machines that can attach to these filaments and move cargoes, for example, along these filaments. And here you see a first point where this polarity of these filaments is very important, namely the direction of motion of these motors is really set by the orientation of these filaments. So a given kind of motor will always walk towards one of the two different ends. And they are usually called minus and plus end. And this is because you can have situations where usually the filaments will grow faster at one end than at the other, will have a faster dynamics at one end than the other, and this faster end will be called the plus end and the other one minus end.
Much larger than KT?
Oh, it's about 30 kT, so it is much larger, yes. And this is the important point, how energy is fed into the system. It's due to the hydrolysis of ATP, so the A is standing for adenosine. This is really one of these 4 letters that you have in your genetic alphabet. There are also interesting connections here. And by attaching 3 phosphate groups, you generate a very stable, energy-rich molecule. And then by cleaving one of the phosphate groups of this molecule, you liberate chemical energy, which can then be used to perform, for example, mechanical work. Now, everything that you have eaten just for lunch has been transformed or will be transformed, at least the energy part of it, into ATP. And this is really the general currency of energy that is used by cells. Everything is first stored in ATP and then transformed into other potentially useful processes. And so these two features, the polarity of the filaments on one hand, but even more the activity as defined by this energy fed into the system on local scales, this is really what endows the cytoskeleton with physical properties that are alien to the conventional materials that we are used to study. And you can study now cytoskeletal phenomena, active phenomena on various scales. So you can start, for example, on a molecular scale by trying to understand how do you generate from chemical energy directed motion. This is not what I'm going to discuss, but I would like to at least show you one other part where this local feeding in of energy creates something which is uncommon to usual physical situations. And that is when we look at the assembly of these actin filaments. And I'm just talking now about actin filaments, but similar concepts also apply to microtubules. And the important thing is, so as I said already, you have 2 different ends with different rates, where usually the ones at this one, the barbed or pointed or plus end, will be much larger than at the other one. But of course, the chemical energy that you need to attach or detach one of these monomers, subunits at one end or the other end, they are the same because everything is identical, right? But now, these assembly rates, they also depend on the state of these monomers. And with the state of these monomers, I mean the following, namely that these monomers, subunits, they can bind ATP or ADP, or a form which is called really ADP plus the inorganic phosphate. It's already separated, but they're still together, not forming one molecule anymore. So the state of these subunits of the actin, the G subunits, this is why we have a G here, their properties really depend on the status of the nucleotide that is bound, if it's ATP, ADPPI, or ADP. And together with these properties, you can generate a situation that is called treadmilling. And with treadmilling, I mean that at one end, the plus or barbed end, really shows net growth, whereas the other one really shows net shrinkage. So you have a net addition of monomers at one side, and you take them away basically at the other side. So this is a situation that is not known to passive polymers, as far as I know. Cannot have that, right? And so in stricto sensu, many people say that treadmilling is a little bit more specific, namely that also the rate of attachment of monomers here is the same as the rate of detachment of monomers at this side. And you can generate this And this can then lead to really nice features that are alien to usual polymers. Namely, you can have, for example, unimodal length distributions. So this would be a length distribution obtained from a stochastic description of these processes that I was mentioning before. And you see that really you have nice length distributions with a maximum that is far away from zero, very unimodal, and here the length is, at least in this, for this parameter values, the length is zero, basically never occur. And this is what people usually have in mind when they say treadmilling. So you have a filament that is moving in space with growing of one end at the same rate as the shrinkage of the other end. It turns out, however, if you really plug in the rates that have been measured, actin never does this. So all these images that you have in mind where actin is really doing this treadmilling motion basically are wrong, in the sense that you can have situations where actin is growing on one end and shrinking at the other, but usually it will either grow faster on one end and shrink slower at the other one, or vice versa. And these two cases, they occur depending on what kind of associated proteins you have in the system, but really this pure treadmilling you will basically never see. Okay, but that's not the only interesting thing that come out from these feeding into the assembly of energy into the disassembly process of the filaments. You can also have interesting phenomena if you look at many filaments together. So this was a single filament basically. Now let's see what happens if we have many filaments together. So what you then see often in cells, and this is now reported really very often in papers nowadays, is that you see waves appearing. So what you see here is actin that has been labeled with a fluorescent dye, and you see that there are bands of high fluorescence moving through the system. So these cells have been treated, they have basically no microtubules anymore, and then you see suddenly these waves appearing in the system. And they are presumably polymerization waves, so waves of assembly of actin that move through the cell. You can have similar phenomena also in other kinds of cells, so these are very different cells from these ones, doesn't matter what they are. Here you see again these wave phenomena. Here specifically the plus ends, so the growing ends of actin filaments have been traced, and you see that these that you have bursts of actin polymerization. So here, for example, and you see these spreading waves in the system. You see them also in human cells, so in our cells. So currently, while you're sitting here, there are some cells doing this in your body, right? So here it's not the actin itself that is labeled, but a protein that is associated with actin which helps to generate new actin filaments. Again, details are here not important. But again, what you see are really wave structures appearing in the system. And I'm mentioning all these things for a reason that you will see on the next slide. As a last example, and quite different from these three examples, I will also give you an example of a wave where mechanics really plays a role. So these are all polymerization waves, so it's really kinetics. Whereas here you see a cell that is spreading on the substrate. So here is the leading edge of this cell. And I hope you can see, at least from the front, you will be able to see that there are some ruffles that are moving backwards, so contrary to the direction of spreading of the cell. And these are supposedly really waves that are due to the action of molecular motors that contract the system locally. We'll come back to that later too. But I would like, for the next two slides, focus on these processes. And as I said, this is kinetic phenomena, so how can we describe such a system? Well, we use a description of the distribution of filaments. We assume that these filaments are rigid rods. We track basically the position of the minus ends of these rods. And then, since they are straight objects, they have an orientation in space. So this is indicated by this unit vector u here. They have a length that can change. And also these densities obviously depend on time. And now what you can do is you can let yourself inspire by all these microscopic processes that I've been mentioning before, and you can write down equations that govern the dynamics of this one. Specifically, I will not write down any equations now, but I would just like to mention what kind of processes we have been considering, for example. And that is, so I told you that these filaments, they grow, but they also shrink again, they disappear, and you have to create new filaments. right? Otherwise, the cell would be empty at some point. Now, at the concentrations of actin in the cell, basically they would never spontaneously assemble and form new filaments, but instead you have to have some proteins, so-called nucleating promoting factors, or nucleators for short, that generate new filaments. And we were interested for reasons in a very specific one that has the following property, namely it's inactive when it's floating around in the cytoplasm, so in the region above the membrane, but once it's on the membrane, then it's active. So for example, here you see some of these nucleators sitting on the membrane, being active and generating new filaments. Once filaments are there, however, then there's a feedback mechanism on these nucleators inactivating them and thereby detaching them. So what you in total then have is a sequence of attachment of these monomers to, and thereby activation of these nucleators to the membrane. This attachment is cooperative, generation of filaments, and then detachment of the, or inactivation of these nucleators to the filaments. Now, if you formulate the equations to that, then you can analyze what is happening, and indeed these processes are sufficient, and I'm not going to explain anything of that now, to generate waves. So here you see the waves of the active nucleators, and here the corresponding presentation of the filament plus ends, and you really see that you can have these nice waves. Now, why should you be interested in the context of this workshop in these waves? Well, these waves have been suggested to be able to orchestrate the cytoskeleton during cell motion. And in order to study this, what we did is we took our system and then encircled it by a boundary, which is here given by this red line. And we basically used this line, which is itself deformable. It has a surface tension, it has a bending energy if you want. And so this line is basically confining our filaments to this space inside this thing. And now you can just see how these waves self-organize in the system. And for these parameters, you will see that the whole system takes up a state where it basically is not changing its form anymore and moving at constant speed in a certain direction. And so this is really what these biologists had in mind, that they say, okay, these waves orchestrate the cytoskeleton in order to generate cell locomotion. This is what you have here. The polymerization of filaments against this boundary in this coordinated wave, where this coordinate wave emerges spontaneously, can really drive such an object forward. Now, even though this has quite a lot to do with our workshop, I would rather not talk about this system today, because here mechanical interactions, they are really confined to the boundary. And so I would like to rather talk about something where mechanics plays a role in the system everywhere in the bulk, and this is why I would like to skip this one here. And the system I would like to talk about is the actin cortex, as mentioned also in the title. So now you know already what actin is. You have seen where actin is acting in the cell. Now, what is the cortex? Well, the cortex is a cortex. So there is a thin layer of actin, highly concentrated actin, around the periphery of the cell. So this would be a cell in suspension, not sitting on a substrate. And then most actin you will find really beneath beneath the outer membrane of the cell in a fairly small layer. And so eventually the question we would like to ask is, well, how is this organization coming about? What makes the actin go to form such a layer? And before that, I would like to just show you that even though I'm showing here a static picture, by the way, this is a picture of a cell that is about to divide. So you see here again in green and in blue the DNA, and in green the microtubules that are about to segregate the DNA, but this is not important for the following. So we would like to study a little bit what processes are going on in the cortex. And so you can do that by shining a laser light, for example, on that. And if you have fluorescently labeled proteins, then you can, by shining light of a sufficient intensity on it, you can destroy the fluorophores without destroying the cell. And then you can see, well, how does this fluorescence recover, if at all, and then you can try to make estimates about the dynamics of the filaments that are underlying. And so this is what we've done here. So you see here this bright stripe, which is the cortex. Then you use the laser and you bleach whatever has been here. So you see that there is no bright stripe anymore. And as you go further, then you see that the light comes back. And so you see, even though it has a static appearance from the outside, in fact there is constantly turnover of actin going on. And the turnover time is about 60 seconds. So every 60 seconds the whole cortex is really renewed. And so in light of these findings, in light of this dynamics, we would like to know then really what are the processes, what is the mechanism underlying the formation of this active layer of the cortex. Right? So again, to summarize the processes that we think are important, we have polymerization of actin filaments at the surface. So this is like in the case of the cell locomotion, right? So you have these nucleating proteins sitting on the surface. You have disassembly everywhere, so the filaments just disassemble in the bulk. And we have something that I've not been talking about yet, namely you have contractile stresses in the gel generated by these molecular motors. So these are depicted here schematically by these little black things. So I told you that molecular motors are proteins that can walk along these actin filaments or microtubules, transport cargo. What can also happen is that these motors come together in small clusters, and then they are able to cross-link filaments. And since they are active, they can still move the filaments with respect to each other, and this overall can lead to the generation of stresses in the system in this active manner. Now, it is rather not obvious how you use these molecular processes in order to really generate contractile stresses in the whole network. This is maybe surprisingly difficult to really understand that. There are some people interested in that. We will not discuss this today, but rather we will take for granted what we know from experiments, namely that stresses can be generated due to the action of the motors. Now, how do we want to describe the system? Well, as I said in the title, hydrodynamics. So what I would like to do is now to review very quickly with you how we come about hydrodynamics for simple fluids and then extend this to this active fluid, because this is how I would like to view the cytoskeleton here, namely as an active fluid with some features that are rather unusual to usual fluids. So what do we do if we do hydrodynamics? Well, we have to identify the hydrodynamic modes. Where do they come from? Well, the first source of hydrodynamic modes are conservation laws. So if we have a simple fluid, what do we have as conservation laws? Well, we have mass conservation, sure. We have momentum conservation, also sure. And then we have a third conservation law, namely energy conservation. Well, all the systems I will be discussing will be at a fixed temperature. So energy conservation will not be important, so I'll just neglect that at all. Okay, mass conservation, well, the flux of matter is just given by the velocity times the density. And here momentum conservation, the momentum flux density is nothing else but the stress tensor, and it's the total stress tensor that we define in this way. It's a tensor of second order, and we have here G, our density of momentum. If we have external forces, then obviously they act as sources. This is nothing but Newton's law, right? So second law. But we will focus here on situations where we have no external forces. So in all what I'm going to say in the following, there will be no external forces. Okay, so what do you do then? Well, then you make the assumption of local thermodynamic equilibrium. So you can define a density of free energy, which I'm going to write in this form here. So we have these small volume elements. They have a certain kinetic energy, and they have a certain internal energy. And then we get the total free energy from integrating over this density, obviously. And then what we're looking at is the production of entropy in the system, which, under constant temperature, in the absence of external forces, we really have only just the negative of, and there's a dot missing, I'm sorry, so there should be a time derivative here, of the free energy. And then you just take the form that you put in, you turn the crank, and what you end up with is a form such that you have written the entropy production as an integral over a product that contains two factors, and one of the factors we are going to call a generalized force, and the other one a generalized flux. Which one is which? It's up to your taste, basically. So this part here is the total stress tensor that you knew before, and this here is the hydrostatic pressure. This one comes in because at some point you use the Gibbs-Duhem relation to replace the chemical potential that comes about, because this one depends on the particle density essentially, and thereby you generate here this difference, which we call the deviatory stress. So this is all that is non-equilibrium, non-static if you want. And then the last step, what you do is you take the fluxes, so in our case the deviatory stress, and you express this in terms of the forces, for which we took here the rate of strain tensor. So this I should have mentioned before. I'm sorry about that. I didn't do that. So the V, alpha, beta, these are the gradients in the velocity field, right? Okay. So we express this thing. So this is now, in principle, this is horrible because this is a tensor of rank 2. V alpha beta is also a tensor of rank 2. So we have a quantity with 4 indices relating these two. But since we are in an isotropic fluid, we look in Landau's book or wherever, and then we know that we can replace this rank 4 tensor by basically two constants, the shear viscosity and the bulk viscosity. And this then gives us, as we know it, the dynamic equations, Navier-Stokes equations. So this is all what we know. Now what we would like to do is to extend this to active fluids. And the extension to active fluids is rather straightforward, because what I'm now doing is I'm incorporating into my free energy also the distributions of ATP, ADP, and PI, and allow for reactions between them. And again, if you do all the calculations, which I spare you here, then basically you end up again with an expression that is very similar as the one before. So you have a sum of products of two factors. This one we know already. This is the one we had from the passive fluid. But then we get an additional product. And this is here, R is the rate of ATP hydrolysis, so it's the rate at which the reaction occurs, times the difference in chemical potentials of ATP, ADP, and inorganic phosphate. So if this one is different from 0, then you will drive this reaction and you will have a non-zero rate. Now the interesting thing is that when I now express my fluxes in terms of the forces, then I can have cross-coupling. So I can have a coupling of this force to this flux, and of this, and vice versa. So I spare you the equation for R. We are not going to be interested in that, because basically what we're going to assume is that the delta mu is constant in our system. Space and time dependence is not present for delta mu. So now if I express my deviatory stress in terms of my forces, so the rate of strain tensor and the delta mu, then I don't have many choices. So I first have the part that I had before, it's an isotropic fluid for the time being. And then I have to couple also the delta mu. Well, since the system is isotropic, the only way I can couple it is in this way, right? I mean, this is what Curie tells me basically, and I'll call the coupling parameter zeta. So these are the forces, and this is the flux that I'm interested in. I should make one statement about the sign. So by our convention, with all these signs that we have used, zeta delta mu, if this one is negative, then this corresponds to an active stress. So basically we will have that delta mu is positive, so that we drive really the hydrolysis of ATP. So zeta basically should be negative in order to get contractile stresses. Again, I'm not saying anything about the microscopic mechanism. It's just a phenomenological parameter that should be obtained from experiments, or if you can, from microscopic theories.
So the active stress in your case is that stress?
Yes, I'm coming to this as you're too fast, but this is exactly what you see here. Thank you. So if you write down force balance, which I did here, then basically you just get a modification of the pressure, and so you also see that this is quite a boring term, because this is only present at the boundaries, because I said delta mu should be just a constant. So in this sense, if you have an infinite system, it wouldn't change anything if the zeta is a constant. And this is what you would assume in standard pure hydrodynamics, right? I mean, all these constants are constants. So I will deviate from this pure theory, from this thing, and I will say that this zeta really depends on the state of the system, in the sense that it depends on the density. So why should it depend on the density? Well, I will maybe tell this a little bit later, but this is what we're going to do. So now let's apply our general formalism specifically to the actin cortex. So we start again with mass conservation. This is the sketch, and I will restrict myself first of all to a situation where we are invariant with respect to translations along the membrane here. So then everything becomes basically one-dimensional. We have only a dependence on the coordinate z, which is the distance from the membrane here. In addition to mass conservation, well, I mean, mass conservation would be just a zero here in its pure form. But as I told you, there's depolymerization going on everywhere. Now, this tells me that I basically should not use this kind of description. Why? I mean, what I've described for you so far is really a situation where I have a single component fluid, right? What I should really do is to give you a multi-component description where you have, let's say, for example, the actin network as one component, and then the solvent as a second component. And then you could have exchange between the solvent and the actin gel, so you could have the actin monomers and the solvent, and this is what you should do. You can do that, but then if you look at the numbers and compared to what is known experimentally, then you can see that this is basically in the right limit equivalent to this one component description. So basically you can assume permeation is not really that important, so you can assume that the background fluid is immobile, and you only have here a description of this effective component, which is basically the actin gel. And for this we know that we have this depolymerization going on everywhere, so we have this sink term here on the right hand side. Now obviously I also need a source term somewhere, otherwise I would just lose material and the state would be boring eventually. And this now comes into the boundary conditions, because I told you that filaments, they do not nucleate by themselves, but they really nucleate, are generated through these nucleating factors. And so we have here a boundary condition on the flux that is non-zero, but it's given by the density of nucleators times the polymerization or nucleation velocity. So this is something that you will not encounter in the usual hydrodynamics problem, because there obviously when you have a boundary which is impenetrable, then you would have a zero flux. Here instead you introduce new material at the boundaries. Okay, so these are the two equations that we got from mass conservation. Now we still need to consider momentum conservation, that is force balance. The general form I've repeated here, but again we are only in 1D, so we end up with this description here. And now what we still have to determine is pressure. So we have obviously a so we have a compressible system, sorry. At least the densities can change. So we have to write something for the pressure. If you think about this two-component description, it would be something like an osmotic pressure, but forget about that. And so what we are going to do, we are going to expand it in terms of rho of the density. Now this form is not really important. I mean, it can be many things. We use this because it's convenient to calculate with that one, but otherwise you can forget about the specific form. What you cannot forget about is that this P can have a non-monotonic dependence on rho, on the density. And so we take this one, this prefactor A, to be dependent on the activity, so this one can become negative, and therefore you can really have a non-monotonic dependence, whereas this beta term is just, the B term is just a stabilizing term. If you get too high densities, then you want the pressure to prevent them from becoming still higher. Now you... Yes, so now why should it start from Q? The idea is being the following. So if you have motors and filaments, you need two filaments to come together. This would give you a rho squared. Now the motor distribution, we assume that they instantly adjust to the filament density, so it's basically imposed by the filament density, so this is why you get another rho, and this is why you have the rho 3. Otherwise there's nothing special about that. Yes?
Already hidden in this F0 that you mentioned before?
Well, no. I mean, there you need a constitutive relation for the pressure in addition. And this is the equation of state that you have to provide, right? This is not coming from.
It's not in the free energy order.
Okay. Good. And now, the nice thing is everything is so simple that you can calculate everything you want. For this, it's very helpful to introduce this function here, which is basically the depolarization rate minus the depolarization rate minus the pressure. And if you do the calculations, then you find that you can express it in the form derivative, so that the slope of the density can be expressed as a function which depends only on rho times this f of rho, where a of rho is always positive. So all the interesting parts here are, and that is the sign of d rho by dz, they are really determined by f. And so let's see what we get. So assume first of all that this activity is small in the sense in its absolute value, so it's not very negative, right? So in this case you can still have a non-monotonic dependence of f on rho, but it will always be negative. And if it's always negative, well, then you see here rho will always decline. So if you want, you can interpret this as a time evolution equation. At least I like this to view it in this way. So this is the density dependent on, let's say, time. You start with an initial condition. You now know that this is always negative because a of rho is always positive, f of rho is always negative, so you will always slow down, and as a function of time you will just reach zero. So there's nothing special, nothing surprising, extraordinary about that. Now the nice thing happens, in the case when f has zeros, and this it can have because it has this non-monotonic character, right? So if you make a sufficiently negative, or its absolute value sufficiently large, then you can have two zeros. One I will call rho 1, and the other one rho 2. Now I will call this one rho 1 because this one is the stable one. How do I see that? I mean, if I start with an initial condition in here, what would you have? You would have a positive rho. d rho by dz would be positive 2, so rho would increase. So you would, by going away from the membrane, you would go closer and closer to rho 1. If you start above here by the same argument, but now f of rho is negative, you would move towards this one. So rho 1 would be, if I view it again as a dynamic system, would be a stable fixed point of this dynamics, whereas rho 2 would be an unstable point. If I'm starting here, I'm going away. If I'm starting here, I'm also going away. So that's already not bad. So I will reach eventually these steady states where I'm going to expect some plateau values. Now I can make a further statement. I can calculate the velocity, and the velocity is given in this way. So what you see here is that the velocity is always positive. So I'm only moving away from my membrane. But if f becomes 0, well, eventually I will have also velocity 0. And so I cannot really go past these zeros that I've created before. And here, just to illustrate this, for 3 different initial conditions. So blue would be an initial condition, whereas you are below the unstable fixed point. So you will reach a constant velocity at infinity. And here would be 2 values. And the black one would be an initial value where you're just in between the 2 zeros, and for red you would be beyond the stable fixed point. And now, what kind of profiles does it generate? So this is the really nice thing. Well, as we saw, so for this blue, you will just get, as before, this gradual decay, continuous decay towards 0 density, but not for the other ones. As soon as you are above the 0 rho 2, which is somewhere here, then you will have motion towards this plateau, and in steady state, and this is what we are calculating here, you will have this plateau, small one here, and then you will have an abrupt fall down to 0 density. So you really have a very nice, well-defined layer. Here too, you start with some density, it reaches the plateau density, and then at some point, whoops, goes down. So these have been obtained numerically, but we have checked if you plot the solutions I have shown you before, you get the same thing, right? Well, a minor detail, depending on this value here, you get either 0 slope at the end of the slope of this plateau, or you get infinite slope, something that also comes out in numerics and that you can show. So here I've changed slightly notations. Just before I was talking about a transition, a bifurcation. Now I would like to to call this an active wetting transition because it has some features of active wetting, right? I mean, of a wetting transition. So as soon as the interaction between the molecules among themselves and the surface are strong enough, you really form a nice wetting layer, or pre-wetting layer, whatever you want to call it. And this role is here played by the active stress in the system. Yeah? As soon as the active stress is large enough, you really form this nice condensed layer, which I guess in analogy you can call it an active wetting layer, and I think it's worthwhile to explore and try to explore this analogy further.
What are the boundary conditions on the velocity?
On the velocity, it's equal to the polymerization velocity at the membrane, and then whatever. And there's only one boundary condition. And this is why you can have infinite, at a place infinitely far away, you still can have a non-zero velocity. The flux is zero, so it doesn't matter, but the velocity can have a non-zero value. Okay, so then you can determine the length of this, or the thickness of this layer that is formed as a function of the actin density at the membrane. And so you see it starts at some value, and this value is just given by Vp over Kd, and this is independent of the form of this F, of the pressure that we've used. Then it decreases, then starts to increase again until you reach the second, now the stable density, which is rho 1. Then again you have the density Vp by Kd, and then afterwards it will just grow ever on. You can make an estimate around this point. The density should go like rho 1 divided by rho 0 divided by rho 1 times Vp over Kd. And if you just by naivete or whatever you want to call it, extend this line, then you see it's not a too good but also not a too bad estimate of the dependence of the thickness on the initial density. So what I've started now here is to look at the dynamics of how such a layer evolves. So we start with a non-layer, so this would be the final steady state distribution, and you see that it's just a front that is moving into this profile. So trying to understand this a little bit more. This is independent of the initial condition, right? It's just always this profile moving, or this front moving into the steady state profile. Okay, so maybe I take 5 more minutes. So I was telling you now about the cortex, neglecting one thing, or two things. One thing is I neglected completely that you have an extension also lateral to the membrane, and you might worry if the system is stable and against perturbations. Well, I've also started to look at this here in Cambridge, and the code seems to work now, and it seems to indicate that at least for these values here the layer is really stable, but this needs to be confirmed. But there's a more important thing probably that I've forgotten. I was making several remarks about the polarity of the cytoskeletal filaments in the beginning, and I didn't introduce polarity at all here. And I think for the cortex it's okay. In general, however, if you want to describe the cytoskeleton, you have to take polarity into account, and let's just spend a few minutes on how you can do this within this framework. And it's a pity that Daryl isn't here, because there's one remark I would like to make for him, but come to that. So again, we start with mass conservation, momentum conservation, and now we will have to take into account also angular momentum conservation, and the free energy will depend now not only on the density of our fluid, but also on the orientation of so on the polarization vector and derivatives of the polarization vector. And if you again turn the crank, you come up with the constitutive equations, and these, I guess, are basically familiar to you if you work with pneumatic liquid crystals. So forget about this line and forget about this term. Then basically what you see here are nothing else than the pneumatodynamic equations, right? So you have the equations for the, I'm sorry, this is now used to be V alpha beta, so the rate of strain tensor. You have the coupling to the molecular field and to the polarization, if you want the pneumatic order parameter to some extent. I mean, polarity doesn't really play too much of a role here. And here you have the time evolution of the polar order parameter. And this is the remark I wanted to make for Darrell. Also here, by just turning the crank, doing nothing else, you end up here with the correct derivative, which is, in this case, a co-rotational convective derivative, right? I mean, there's nothing that you have to put in addition, and you don't need all these complicated things that he does. But then we have here our additional terms, and so you recognize again our delta mu. But now, since we have this polar order parameter, we have anisotropy in the system, and we can have more interesting couplings between the stress and delta mu than before. So we have the isotropic term that we had before, but we can have also these anisotropic terms. And we have also an influence of the activity on the orientation of the polar vector. And this would be, for completeness, the equation for R, but again, this we neglect usually. And so to give you one application of that is what we call the Taylor-Coet motor. So you have the Taylor-Coet geometry, so you have two cylinders that are free to rotate. Everything is at low Reynolds number, I should emphasize. I haven't emphasized this before, but maybe this goes without saying. Everything we did here was at Reynolds number equal to 0, right? And so we look at so we define the torque that we apply to the system per unit axial length to be called gamma. Gamma minus would be at the inner cylinder, gamma plus at the outer cylinder. Since we want to look at a torque-free system, at least in the beginning, this would mean that the sum of the two vanishes. We take the polarization vector to have a unit length, and just can specify it by its angle towards the radial axis. We will look at a system that is invariant under rotations, and we look at an incompressible system. And without showing you any further equations, this is what you get. So again, depending on the activity, if it's large enough, in the sense large enough negative, right, then you see that at some point the quiescent state becomes unstable, and you get a bifurcation towards a rotational state. So what you see here is we clamp so we have strong anchoring conditions. We have the psi equals to pi over 2 at the inner, at the outer cylinder. We have a high activity of 100 here, so we are already here. And then in our reference frame, we have the velocity 0 at the inner cylinder, and we have at the outer cylinder a velocity. So you have spontaneous motion, and this thing starts to turn spontaneously. This would be a similar state, but now the polar order, or the angle has a 0, has a node here, but this one is one of these unstable states. Now, if it's really a motor, you want to be able to perform work against an external torque. So, and this is what you can see here. So we plot here the torque that we apply, and here we have different activities, and this would be the frequency at which the system rotates. So in the beginning, you have what you expect also from a passive system. This thing rotates in the direction where you apply the torque. Then if the system becomes supercritical, that is, we can have an instability, the system starts to do work, and then you can have also for negative torques, positive velocities, so the system is really working against the external torque, so you can build a motor with that. And then, which I find funny, maybe not too deep, I know, is that here this stable branch goes really down, so you again will have, even in this active regime, for negative torques, negative velocities, and you can have several unstable branches in the beginning, so it really rounds up, so you can have really a kind of very messy pattern inside, but that's maybe not so important now. Okay, and this is, I guess, what I wanted to tell you, just to summarize. So I hope that I could give you the impression that the cytoskeleton is really a rich source of many physical problems. You can address them on very different lengths and time scales, starting from problems that are really at the level of single molecules of the cytoskeleton up to really collective phynomena. We can capture generic properties of the cytoskeleton by this hydrodynamic description. I mean, you might wonder if such a hydrodynamic description is really applicable on the scale of a cell, right? I mean, so you have a mesh length of a few tens, hundreds, nanometers. The cell itself has, let's say, 10, 20 micrometers in extension. So you might really wonder if you can use these concepts. If you do, you can still try to get those generic properties, and surprisingly often they tell you really something also about what is going on in the cell itself. By the way, there are also cells that are really big, almost as big as this room. Physarum polycephalum became first in Japan and now back again also in Germany, a model organism for studying cytoskeletal dynamics. And they are really length scales so large compared to the fine structure of the cytoskeleton that you can definitely use hydrodynamics. And yeah, well, I was trying to put forward this idea of viewing the actin cortex as an active wetting layer, trying to argue that really the contractile activity of the system generates, in spite of the turnover that you have in the system, the well-defined layer. And with this I would like to thank you and close the talk.
So in your mechanism to get a confined layer of actin filaments, so in that model the active stress was still isotropic, right?
Yes.
So then the compressional part is a bit, so that is important in keeping the system confined, but it's a bit puzzling to think that this is due to the activity of the motors, wouldn't you think?
Why?
Well, because the activity of the motors is some kind of tangential, no? And
well, no, not only. I mean, you have these things. So we neglect the polarity. What you should do, of course, would at least allow for some small directionality, because the filaments, they grow away from the membrane. So you will also have a component that is not tangential.
But then I would say that there's a more obvious source of that stress, which is growth, polymerization, and you're adding mass.
Okay, so what we do not discuss here at all are elastic effects. I mean, obviously the system is viscoelastic. If you want to introduce the elasticity on short time scales, this whole thing becomes a real mess. People can do that, have done this. We have also done this. And then Frank Jülich and Andrew Cullen-Jones were the ones, I think, who did it correctly now. There might be also effects due to that. But here we're looking at the long-term limits, and maybe they are not so important. I mean, there are also, in addition to the molecular motors, there are other proteins that can cross-link. These cross-linking proteins, however, they have a shorter lifetime than the motors. So turnover is even faster. So, but I mean, you can also just get away from the molecular picture and just say, okay, there are stresses generated in whatever way. I don't care about the molecular mechanisms. This is captured by the zeta delta mu. That's a nice thing, right? I mean, whenever you say it's not this mechanism, I say I don't care, because as long as we have it, then you will get this phenomenon. But I agree that it's also interesting to look at molecular mechanisms. I mean, that's definitely true.
In conventional hydrodynamics, dissipative terms related to thermal noise. Should I know something about noise? Or
You should. But I don't know how to introduce it here. I mean, in a consistent way. I mean, this can be done if you start from microscopic models, obviously. How to do it here in a consistent way, I don't know. But I think it's still an open problem.
Can I ask about the last problem? Are you actually driving it by moving one of the cylinders?
Well, no. In the first slide that I was showing you, we did not. So in this one, it's zero torque transitions, so there's nothing. So it starts to move spontaneously.
Right.
But in the second one, well, whoops. Here it's torque free, and here everywhere else you have it.
So why does it choose to go round and not say up and down, or a spiral? Could you get a spiral? When
Probably you can, but so maybe I wasn't explicit enough about it. So we assume that the system is invariant with respect to translations along the axis and with respect to rotations.
Yeah.
So we are quite restricted. And so we are now doing an analysis where we take also the rotational degree of freedom into account. And for the time being, it seems that these ones are stable solutions.
Right.
Many of them.
But not the longitudinal.
Longitudinal,
yet.
Yes, well, I mean,
Yeah.
that's more difficult. But we expect certainly to have more interesting dynamics then.
Okay, well, thank you very much. We'll have